steadily, apart from the engine noise and the slight vibrations, you would have no way of telling that you were moving. Life carries on inside the plane exactly as it would if it were stationary on the ground. We say the plane provides an inertial frame of reference. By this we mean Newton's law of inertia applies, namely, when viewed from this reference frame, an object will neither change its speed nor direction unless acted upon by an unbalanced force. A glass of water on the tray table in front of you, for example, remains stationary until you move it with your hand. But what if you look out of the aircraft window and see the Earth passing by underneath? Does that not tell you that the plane is moving? Not really. After all, the Earth is not stationary. It is moving in orbit about the Sun. The Sun itself is orbiting the center of the Milky Way galaxy, and the Milky Way galaxy is moving about within a cluster of similar galaxies. All we can say is that these movements are all relative. The plane moves relative to the Earth. The Earth moves relative to the plane. There is no way of deciding who is really stationary. Anyone moving uniformly with respect to another at rest is entitled to consider himself to be at rest and the other person moving. This is because the laws of nature, the rules governing all that goes on, are the same for everyone in uniform steady motion, that is to say, everyone in an inertial frame of reference. This is the principle of relativity. And no, it was not Einstein who discovered this principle. It goes back to Galileo. That being so, why has the word relativity become associated with Einstein's name? What Einstein noticed was that amongst the laws of nature were Maxwell's laws of electromagnetism. According to Maxwell, light is a form of electromagnetic radiation. As such, it becomes possible, from a knowledge of the strengths of electric and magnetic forces, to calculate the speed of light, c, in a vacuum. The fact that light has a speed is not immediately obvious. When you go into a darkened room and switch on a lamp, the light appears to be everywhere, ceilings, walls, and floor, instantly. But it is not so. It takes time for the light to travel from the light bulb to its destination. Not much time. It's too fast to see the delay with the naked eye. According to this law of nature, the speed of light in a vacuum, c, works out to be 299,792.458 kilometers per second, or very slightly different in air. And that's what the speed is measured to be. What if the source of light is moving? One might, for example, expect light to behave like a shell being fired from a passing warship, where an observer on the seashore would expect the speed of the ship to be added to the shell's muzzle speed if being fired in the forward direction, and subtracted if being fired to the rear. The behavior of light in this regard was checked at the CERN or CERN laboratory in Geneva in 1964, using tiny subatomic particles called neutral pions. The pions, traveling at 0.99975 C, decayed with the emission of 2 light pulses. Both pulses were found to have the usual speed of light, c, to within the measurement accuracy of 0.1%. So the speed of light does not depend on the speed of the source. It also does not depend on whether the observer of the light is considered to be moving or not. Take the case of a moving vessel again. Having already established that light does not behave like a shell being fired from a gun, we might expect it to behave like the ripples on the water. If the observer were now someone aboard a moving boat, the wave front would appear to move ahead of the boat more slowly than the wave front going to the rear, because of the motion of the boat and of himself relative to the water. If light were a wave moving through a medium pervading all of space, a medium provisionally called the ether, then, with the Earth plowing its way through the ether, we ought to find the speed of light